Okay, our next topic is hydraulic turbines. Already we discovered our hydraulic machines of both pumps and generalized discussions of hydraulic machines. Now we will go for our main topic, hydraulic turbines. So the hydraulic turbines, mostly hydraulic turbines uses a potential and a kinetic energy, both potential and kinetic energy of water, and converts into the useful of mechanical energy. So the hydraulic turbines uses both a potential as well as a kinetic energy. The potential energy we are getting from the dam. So already we discussed already completely about the layout of hydraulic power plant. So in the hydraulic power plant, the hydraulic dam is constructed at the flow river path. సో ఎక్కడైతే మనకి ఫ్లో రివర్ పాత్ ఉంటుందో అక్కడ డ్యామ్ కన్స్ట్రక్ట్ చేస్తారు. ఇట్ ఈస్ వెరీ హై లాంగిట్యూడ్ వెరీ హై లాటిట్యూడ్ మీన్స్ వెరీ హైట్. సో the high amount of the high, for example this is a dam, so this is a dam gate. So already we completed all these things in the hydraulic power plant layout. This is a penstock, this is a nozzle and a turbine, all these things. So the high head water is coming from this dam to the in front of this blade. So this energy is called potential energy. There is some height of from the dam to the center line of the nozzle. So this is a H. So whenever the high altitude is there, here potential energy is exists. The potential energy P is equal to mgh. The high potential energy coming from this dam is converted as a kinetic energy at nozzle. So in the penstock, the potential energy coming from the dam is converted as a kinetic energy in the nozzle fitted, because as a nozzle the velocity is increases. A nozzle is reducing cross section area, where is the diameter is decreases, then the diameter decreases, cross section decreases. When the cross section decreases, according to continuity law, the velocity should increase. The more the velocity, more the kinetic energy, that is of mv square. Means at the entrance of the nozzle the velocity increases. When the velocity increases, the kinetic energy increases. So here the hydraulic turbines, the potential energy is converted as a kinetic energy by using a nozzle. So the hydraulic turbines uses potential and kinetic energy of the water and converts into the useful mechanical energy. So the fluid energy available in the is maybe natural or artificial. For example, if the water is coming from the natural, means any natural source like waterfalls, there is no artificial potential energy. It came naturally. So artificial means if we construct a dam is artificial. Okay, the fluid energy is available in the natural or artificial high level of water reservoir which is created by or constructed a dam appropriate in the place of flow path of a river. So coming to the classification of hydraulic turbines. So how the hydraulic turbines can be classified. So let us see how the hydraulic turbines are classified. So the hydraulic turbines is classified into so many accordingly so many ways, and so we will discuss one by one how the hydraulic turbines is. Just wait a minute. So classification of hydraulic turbines. Classification of hydraulic turbines. The hydraulic turbines can be classified in so many ways. The first one is according to the impulse effect. The hydraulic turbines can be classified into according to, the first one is according to effect, means whether it is impulse or reaction, according to effect, or energy, according to energy, that may be impulse or reaction we can classify. And the second one according to according to type of flow, according to the flow through the runner, according to flow through the runner. So how the water is entered to the runner. And the second one, according to the head, according to head and discharge. So discharge and head is vice versa. If the higher the head, lower the discharge is required. Higher the discharge is, lower the head is required. And the next classification, according to the specific speed. According to specific speed of a turbine. And the last one, according to disposition of the shaft. Disposition of the shaft. So in this way, the hydraulic turbines can be classified. The hydraulic turbines can be classified into these are the many ways. According to energy, impulse turbine and reaction turbine. According to the flow through the runner, we can classify as a radial flow, tangential flow, axial flow, and the fourth one is a mixed flow. Again, radial flow can be classified into so many ways. Again, I got into head and discharge, high, medium and low. If the head is high, discharge will be low. If the discharge is high, head will be low, vice versa. Head and discharge will be vice versa. Why head and discharge will be vice versa, we will cover in the next topic. So according to the specific speed, again this is a classified into high, medium and low specific speed turbines. So according to the disposition of the shaft, we can classify it as a horizontal shaft. The shaft is a horizontal, and second one is a vertical shaft. The shaft position is a vertical. So in generally, Francis and Kaplan turbines is a vertical shaft, vertical positioning, and Pelton wheel shaft is a horizontal positioning. So we can go for one by one. So according to the impulse effect, what is the impulse effect, what is the reaction effect? In the first one, according to the energy, the first one, impulse effect. So what is the impulse effect? So available hydraulic energy first converted into kinetic energy by means of a nozzle. So the water coming from the reservoir is through penstock, then it is connected to the nozzle. So in the penstock, the available energy is the potential energy, then the end of the or starting of the nozzle, the available energy means the potential energy. So potential energy coming from the reservoir or dam through penstock. So at the end of penstock, we connected a nozzle. It is a reducing cross section area. So here the efficient nozzle, this is called efficient nozzle. Here what happened? The potential energy is converted into the kinetic energy, because when reducing the cross section area, diameter is decreases. When the diameter decreases, cross section area also decreases. When the cross section area decreases, velocity is increases. That we call as a kinetic energy, half mv square. This means, so the available hydraulic energy means potential energy first converted into the kinetic energy by means of a efficient nozzle. The high velocity of jet issuing from the jet then strikes a curved or series of suitable shaped vanes, fixed vanes on a peripheral of the blade or wheel. So entire fluid machine works on the pure impulse effect, means here only kinetic energy is takes place. I already told that work done is work done is equal to VW1 U1 minus VW2 U2 is equal to kinetic energy plus centrifugal energy plus reaction energy, or nothing but centrifugal effect, kinetic effect, centrifugal effect and reaction effect. Means in the impulse effect only the entire turbine is completely works on the pure kinetic energy. That kinetic energy is called pure impulse effect. There is no centrifugal effect and there is no reaction effect in the impulse turbines. So it operates under atmospheric pressure. So I will explain how the impulse turbine completely in atmosphere. I will explain in a Pelton wheel turbine. So it operates under a atmospheric pressure. There is no pressure change in the turbine render. So it is this the example of impulse turbine is a Pelton wheel. So the Pelton wheel is completely works on a atmospheric pressure. There is no such changes of pressure energy or kinetic energy versus pressure energy, or pressure energy versus kinetic energy, or kinetic versus pressure energy. There is no change of reaction. There is no change. There is no need of reaction. When there is no need of reaction, there is only impulse effect is there. For creating a reaction effect, we have to maintain a closed conduit or closed sealed environment of a turbine. So the Pelton is completely works on the atmosphere. Then there is no need of a draft. No need of a draft tube in a impulse effect. So the available energy is converted completely as a kinetic energy. Only kinetic energy plays an important role. The entire turbine is works on a environment that is called atmosphere. So the example of so in this impulse effect there is no need of a draft tube. The draft tube is needed where a reaction effect is we need for increasing the pressure energy or increasing the kinetic energy, of change of vice versa pressure energy and kinetic energy. We need a closed conduit or closed sealed of a sealed type of environment in the turbine. But if there is no reaction effect, means there is no closed conduit. So when there is no closed conduit, there is no reaction effect is called. We don't need any draft tube for impulse turbines of Pelton wheel. There is no requirement of a draft tube. No requirement of a draft tube. So there are so many impulse effect turbines is there. The most important used impulse turbine is a Pelton wheel turbine. Another turbines is a Tango impulse wheel and Girard turbine, Banky turbine and John Wall turbine. You can refer my notes. There is a number of turbines is there according in the impulse effect. And coming to the reaction effect. So what is the reaction effect? Okay, the second one is a reaction effect. In a reaction effect, both impulse and reaction effect is completely contributed. Sometimes there is a centrifugal effect also contribute in this entire turbines. This means a part of force exerted by the fluid in contact with the blades of this machine is due to pressure change across the rotor blades. Means the reaction effect is nothing but the reaction between the kinetic energy and pressure energy is called reaction effect. So both pressure energy as well as the kinetic energy is plays an important role in the reaction effect type of turbines. So the kinetic energy also plays an important role, and pressure energy also plays an important role. So some turbines centrifugal effect is not there, some turbines centrifugal effect is there, but most of the cases centrifugal effect also we consider. In reaction machines there may be a contribution of impulse action, whereas an impulse machine only pure impulse effect is there. So reaction turbine lo both impulse effect KE and reaction effect rendu unte oka impulse turbine lo matram pure impulse effect matrame run avutundi. So the blades of reaction turbine is a closed sealed from the atmosphere. So intaku mundu chupichanu how the turbines is closed sealed, like Francis and Kaplan. It is different from the Pelton wheel. So already we discussed the animations of these turbines. So the examples of this reaction effect is the most successful and most used turbines is the Francis and reaction turbine, and another type of reaction turbine is Fornari and Thomson and bulb turbines. Mostly in a real time examples Francis and Kaplan are most successful reaction turbines. So when there is a reaction effect is there, definitely we should provide a draft tube. By providing a draft tube, we can increase a more effective head. So for reaction turbine, definitely we should install a draft tube. For an impulse turbine, there is no need, there is no such requirement of a draft tube. These are the most examples of the reaction turbines. In the reaction effect, reaction turbines, both the kinetic energy, pressure energy is a important role. It is changing vice versa. If the kinetic energy increases, pressure energy will be decreases. If the pressure energy increases, kinetic will be decreases. Whatever it vice versa means, if the pressure energy increases, kinetic energy decreases. If kinetic energy increases, pressure energy decreases. According to law of conservation of energy, if one energy is converted to another energy, this is a reaction effect. So in addition to the another type of classification, so according to energy, both impulse and reaction turbines is completed according to the flow. So how the turbines are classified into the according to the flow. According to the flow. So how the turbines are classified into according to flow. So the first one is the tangential flow. Tangential flow, radial flow, axial flow, and the last one is the mixed flow. So in tangential flow, the example is a Pelton wheel is a example of a tangential flow. I am writing examples of tangential flow. Example is a Pelton wheel turbine. Pelton wheel turbine. For radial flow, Francis turbine. Old Francis, not new Francis. Old Francis turbine. For axial flow, Kaplan turbine. And sorry, I didn't remember that. Bulb turbine, yes, bulb turbine and propeller turbine. Mixed flow is a modern Francis turbine. So these are the classifications of type of flow. Tangential flow means this is a wheel, this is a blade of a turbine. The water strikes at the tangent of the wheel. That is called tangential flow. Radial flow means if it is a wheel, it is not a blade, the water enters one radius and leaves another radius. So already I discussed about this is a R1, this is a R2. Means the water enters one radius and leaves another radius. So this is called radial flow. So again, radial flow can be classified into two types. So how the radial flow can be classified? Inward radial flow and second one outward radial flow. So what is the inward radial flow? What is the outward radial flow? Just we see that. So this is a blade on a wheel. Inward means, in the term inward means the flow is completely towards inner. This is center towards inner means the water enters outer radius, leaves from the inner radius, both radially. That is called inward, towards inner of the wheel. So outward means the water enters inner and leaves towards out, that is called outward. Means outward means it flows towards out, inward means it flows towards in, that is called inward flow. Means both inlet and exit, inlet of the blade and leaving of the blade, means both the inlet of the turbine and outlet of the turbine is a same direction, that is a radial flow. This is called radial flow turbine. So inward radial flow is a old Francis, means both inlet and exit of the water flow is a radially direction. So what is the axial flow? Axial flow means, already I told that axial flow, the flow path is exactly parallel to the shaft axis. If it is a turbine, the example is a Kaplan. This is the hub of the Kaplan turbine. This is the blades. So the water flow is a direction parallel to the axis. This is the axis of the shaft. This is a parallel to the shaft. So inlet also parallel to the shaft axis. Leaving of water from the turbine blade is also parallel to the shaft axis. This is called axial flow turbine. Example, Kaplan turbine, bulb turbine and propeller turbine. And mixed flow, I told that mixed flow is nothing but a combination of, mixed is nothing but a combination of any two flow means the inlet, for example, if the inlet of the turbine, the water inlet to the turbine is a one type of flow and leaving from the turbine is another type of flow. Again, this means the inlet to the turbine wheel is a one type of flow, leaving from the turbine wheel is another type of flow, that is called mixed flow. Means both inlet flow, outlet flow will be different directions, that is called mixed flow. So example is a modern Francis. How the modern Francis is for example, this is a wheel. So the water enters radially, radial to the wheel and leaves axially. I cannot represent in a three-dimensionally in a turbine diagram in this board. So for example, so this is a turbine. There is a, so I cannot explain diagrammatically how. Already I explained in the previous animations how the Francis turbine works. The flow is inlet flow is what the direction, the leaving flow is what type of direction. So means the inlet to the turbine is radially and the leaving from the turbine is axially. So there is a radial, there is a axial. Two type of flow is called mixed flow. That is the modern Francis. So modern Francis, the water enters to the turbine casing as a radial flow and leaving from the turbine case as a axial flow. So these are the according to the classification of turbines. And coming to the according to head and discharge, how the turbines is classified according to the head and discharge. So let us see. So another classification of available head according to available head and discharge, and the last one is next one is according to specific speed and according to position of shaft. So according to available head. So now we will discuss about according to the available head. So the turbines can be classified as a high head turbine, which required already told that high head turbine requires a small amount of discharge. So high head turbine, high head is required low discharge turbine, and second one is a medium head is required a medium discharge, and last one is a low head turbine requires a low head means high discharge. So high head turbine is the example of Pelton wheel. This is the example of Pelton wheel. This is an example for Francis, This is for example of Kaplan. So high head turbine. So Pelton wheels requires generally greater than 250 meters. So Pelton will require greater than 250 meters of head, means the head of reservoir to the center line of the nozzle is a 250 meter. So it is required greater than 250 meters of head is available. So for construction of Pelton wheel, the reservoir should be height of above the 250 meter. So for medium head, the head required is 60 to 250 meters of height, and for low head turbines up to 30 meters, up to 30 meters is enough. For a higher turbine, 250 meters greater than is required. For a medium head like turbines of Francis turbine, for construction of Francis turbine, we should in the range of 60 to 250 meter reservoir height should be required. For low head turbines, it's required low head turbines require high discharge. Example is Kaplan. For construction of Kaplan power plant or Kaplan turbine, up to 30 meter is enough for construction of a Kaplan turbine. And next classification is according to the specific speed. Here also low specific speed, high specific speed, and medium specific speed. So as well as you can follow my notes according to the specific speed. Pelton wheels generally requires Pelton wheel having a low specific speed, and Francis turbine having a medium specific speed, and Kaplan turbine having the high specific speed. Again, that is high specific speed or low specific speed or medium specific speed can be classified into so many ways according to slow runner, normal runner, fast runner can be classified. And the last one is according to disposition of shaft. The shaft may be horizontal shaft, the shaft may be vertical shaft. So how the horizontal shaft, how the vertical shaft is mostly vertical shaft is Francis and Kaplan. Reaction turbines where shaft position is almost vertical position, and Pelton wheel shaft position is always horizontal. So this can be this is a classification of a hydraulic turbine. In the next class we will go for Pelton wheel. So how the Pelton wheel is working, how the Pelton wheel is designed, what is the design proportions required for the Pelton wheel, so how the power is generated, what is the efficiency of the Pelton wheel, what is the output blade efficiency of the Pelton wheel. All these are we will discuss in the next class. Okay, thank you.